programar. Ahí está, ahora sí.
Eso.
Ahora sí, esta reunión se está transmitiendo, entendido. Entendido. Finalizando, redirigir.
Ok, ¿estamos?
Ahora,
Okay.
abrimos yo en la pantalla de YouTube.
Comenzamos.
Vamos, Diego.
Hello, welcome everyone. Thank you for joining us today. First of all, let me introduce ourselves. We are a group of students from 9 Latin American countries working in topics related to space geophysics. And last year, during the Alaje conference, Alaje is the Latin American Association of Space Geophysics, we created Interalage, which is the Alaje student network. And since then, we have been working in order to propose activities that could be useful for students. And well, what is this event about, Seba?
Well, this is our first talk. Thank you, Noe. This is our first talk. Here we are inaugurating our cycle of conferences. So we propose this cycle with the motivation of staging that Latin American researchers in the different fields of space geophysics, connecting them. And in this way, different students can know which topics are being researched, which are like the hot topics in our different countries. So in the sense, our first guest, or guest of honor to open the cycle of conferences is Dr. María Graciela Molina from Argentina. Iván.
Thanks for accepting this talk, Dr. Graciela. She is from Tucumán Space Weather, and she works at the Faculty of Exact Science and Technology of the University of Tucumán in Argentina. She directs the Scientific Computing Laboratory of the same faculty and is an associate professor. In addition, she is a CONICET professor. Her main lines of research are ionosphere and space weather, radar systems, and scientific programming. Currently, she works on monitoring and forecasting space weather events using artificial intelligence techniques. Thanks again, and the microphone is all yours.
Hello, everyone. Thank you for inviting me. It is a pleasure to give you a talk. I think this is a good idea for everybody, not only for students in Alaje, but also for researchers and the groups to start talking about what each of us are doing in Latin America, right? So let me share my screen. Let me know if you see my screen. It's okay? Do you see
we are seeing your
okay.
screen.
Yes.
So I'm sharing. Okay. So you will see the full screen now. And so my talk is about machine learning for space weather. So this is our group, the Tucumán Space Weather Center, and this is our Instagram, if you want to check. And as the guys just present me, I am from Tucumán in Argentina. When I was thinking about how to do this talk, I was trying to merge two huge fields of research, so the space weather and the other is machine learning. So I'm going to talk a little bit about the space weather, then I'm going to talk about a little bit about machine learning, and later on I will merge both fields and how machine learning is helping space weather. And finally, I'm going to talk about applications and of course some questions and answers we can exchange. So basically, everybody has an idea here. If you are very close to Alaje, you know what space weather is. And you know there are different kind of definitions, and many institutions have tried to make a definition of space weather. But I took this one because I like the scope of this definition, because it's going to be later easy to relate with machine learning. So we were going to talk about space weather as the physical and phenomenological state of nature space environments. The associated discipline aims, through observation, monitoring, and analysis and modeling, at understanding and predicting the state of the sun, the interplanetary and planetary environments. Among them, the planetary environment is the Earth environment, and the solar and non-solar driven perturbation that affect them. And also at forecasting and outcasting the potential impacts on biological and technological systems. So basically what we are looking now is like a very huge coupled system from the sun, mainly, as one of the main drivers of space weather, and through many and different events that are happening there, how they are affecting our environment. In particular, we are interested in the Earth environment. So here's a nice picture that I took from ESA, and this is a very interesting one because it goes to the idea of the consequence of space weather. So we can have several sources in the sun, like a flare that is triggering a coronal mass ejection, for example, and later on is going to perturb or to disturb the Earth environment, the magnetic field, the Earth magnetic field, for instance, and will then, in like a change of events, we have consequences within our atmosphere. More important for me and for my group is the consequence in the upper atmospheres. So if we think a little bit more into this definition, we can divide this definition in four. I put four like pillars, no? Like the science itself that is involving the sun, the interplanetary and the planet environment, and we are looking at it as a coupled system, no? Not as just physics in the sun, physics in the intermediate planetary environment, or in the planetary environment, but as a whole, as a change of coupled system or coupled system. Then we have the impacts of the space weather, but not only the scientific impacts, let's say, but also what we are interested on, that is what consequences have for us. So we have to take into account stakeholders, look what we call research to operations, and drivers that drives the services for different interested parties, such, for instance, ICAO, which is very interested in high frequency perturbation due to space weather. Another important pillar on this, the study of this field that is space weather, is the instrumentation. What we can talk a little bit about instrumentation. One important point is the coverage of the instrumentation. So we know that we have few instrumentation looking at little parts or partially the system. So if we are looking at the sun, we have few missions that are looking part of the sun, and so on and so forth. So even though that in the last few years we have a lot of for instance, missions, space missions, or we have a lot of GPS station, or we have GNSS receivers that covers almost all the world, and we have a lot more of radars. Nevertheless, still are few that for this huge domain that is space weather. So these partial observations have also different targets, no? So what we can do with this observation, we can do science that most of us are interested on. We have military interest in this field, and also commercial. So there are a lot of parties interested in space weather. Also, another important thing about instrumentation is not only work as different instruments, but to work all together as a network. So they start working on network, for instance, of GNSS. So GNSS systems are networks of satellites that are able, for instance, to measure what is happening in the upper atmosphere. Also, another important point is that space weather is a very complex system, and thus it needs to be tackled as a very interdisciplinary field. We need to nowcast or forecast the different part of the domain. We want to model it, we want to analyze, we want to monitoring, and also we want to observe what is happening. So all this part I just decouple all these parts can be seen from one of the topics that is, in this case, this talk, that is data-driven modeling. So if we're looking at the system and we are looking at the data, we can try now to model this. So here I will talk a little bit more about the main sources and the propagation of space weather events, from the observations to the consequences. So we want to have in our mind like a change of events. And this is important when we are going to model this through machine learning. So many of us are very, very familiar with what are these CMEs, or coronal mass ejections, that are these huge plasma eruptions or releases from the sun that can eventually be geoeffective. So it can arrive to our planet, to our environment, to our near Earth system through the solar wind. So basically, these are the change we are interested in. The consequences are what we call geomagnetic storms, that are perturbation of the geomagnetic fields due to these events, other events, but I'm talking just this one. But what we are interested in from the machine learning to understand them with machine learning, for instance, is that these kind of events are typically slow. And we are talking about slow because they are typically from their source till the consequences in the Earth, we can have several days. So it seems that if we want to forecast this arrival of this event, it seems to be easier. Well, no, it's very complicated. So the effectiveness of the CME is a huge field itself. But it helps us later. Later we will see in some of the examples. But yes, this is a slow event, let's say, compared with the others, right? So then, when a solar flare occurs, if the solar flare is the source in the sun, then which is the solar flare? You know, no, that this is the burst of radiation from the sun and particles triggered by the release of magnetic energy on the sun. So we have different radiation. We have radio, white light, EUV, soft X-ray, and hard X-rays that are, and also particles going towards the Earth if we are facing it, right? So in case of, again, the idea of some effective cases, we have the arrival of several events. So CMEs are associated with these flares. So we have plasma coming toward us if we are talking all the time about geoeffectiveness, geoeffective events. I'm going to talk only about that. And you can have also radiation, X-ray, for instance, coming towards Earth. And you can see it as an enhancement of the X-ray. And this is a fast event that can arrive around 8 minutes to the Earth. But it's going to be effective if you are in the daytime. It's very hard to predict. It's also a huge field of prediction because the difficulty is to predict when a flare is going to occur. And also, the other problem is that you have 8 minutes to forecast, which is crazy because you are looking at it with an instrument near, for instance, in the space, and you are almost there. And when you arrive, they arrive almost with you with your data, with the light, right? So it's very hard to predict. It can produce what can happen in the ionosphere on the upper atmosphere. It can produce a sudden ionization in the ionosphere, mostly in the low regions, like E regions or D regions. So you will see enhancement there mostly. Another thing that we are facing when we have this kind of event is that we can have this storm of particles arriving. And these particles can arrive almost, I think this is a fast event. Sorry, I think this is something that I copy paste, but this is a fast also, like in 20 minutes can arrive to the Earth. I should mention that the flares are not only the only source of this kind of events, also filaments and other things happening can trigger some consequences on space weather. Another event that we are interested in the group is the coronal holes. So coronal holes are this portion of the sun atmosphere with very low density compared with the other, of course. So these regions or coronal holes are like regions when the magnetic field lines of the suns are like opened and connected to the interplanetary medium. So we can, these lines can transport all these perturbations to our Earth environment. This as if we are looking at how fast this can be, they are fast compared with the background solar wind, but maybe it's not as fast as a CME, and we can think that the perturbation in the geomagnetic field can be lower than the CME, but it's not always the case. In fact, we have a paper that we analyze one coronal hole that trigger a very interesting and complex and strong geomagnetic storm. So you can check this if you want. And they can trigger geomagnetic storms. Okay, if we are going to link now the geomagnetic storm to the Earth environment, of course, there's going to be a coupling between the solar wind, the magnetosphere, the ionosphere, and the thermosphere. So thermosphere is also important here, or the low part of the ionosphere to be more accurate. So the lower part is going to be also perturbed. So there are a lot of events coming or occurring at the same time if a geomagnetic storm occurs in the global perspective. So then we have to see what is happening into the ionosphere and to see what is happening in different regions of the ionosphere. What can happen in the ionosphere? So we will see, not in the ionosphere, let's say in the Earth environment. So we can have geomagnetic field perturbations. So we have observables such as the different indexes, like in auroral latitudes, these ones or many more, others like KP, DST, CMH, and many more that are not put in here, but there are a lot of indexes that show how the Earth magnetic field is perturbed. And we have in Latin America one for South America that is KSA. The ionosphere also has suffered some modification of the ionospheric current system at high latitude. So we have look at what we call prompt penetration electric field from the auroral zone, and that this perturbation can be spread to the ionosphere, to the other regions of the ionosphere. Modification of the ionospheric current system at low latitude, the equatorial jet, electron jet, many of you know, ionospheric heating that is causing, this heating is going to cause like the expansion of the ionosphere, and you will see a lot of perturbation in the ionosphere, travel ionospheric disturbances, and many, many more other things. Here there's a little work we have done in 2019 that we analyzed one storm. This is TC. This is TC, and this is delta TC for a region, for a meridional region in America, from minus 50 degrees to 60 to 50 degrees in latitude. And you will see, like when the storm happens, that is, this is the storm, this is CMH, that is similar to DST index, and you will see a sudden storm commencement and main phase of the storm and a recovery phase, and you will see how the DC, or the total electron content of the ionosphere, is perturbed or different at this time. So you will see it's very, very common to see these two crests of the equatorial anomaly, and when the disturbance occur, or the storm occurs, you will see like this superfontine event. We also analyze disturbance and traveling disturbance, traveling ionospheric disturbance from high latitude in the south to the high latitude in the north. So this is high latitude south and high latitude north. So basically we are having this, this is delta DC for each of them. You can check later if you want, you can ask me later. So what is the difference in ionosphere? The difference is that locality matters. So when we are looking at the solar wind and we are looking at the sun, we see something global. But when we go into the Earth, we see more local differences. So the ionosphere can be perturbed differently if you are in the pole or in the equator region. So this is very important. So basically that's the chain of events, and it is very simplified thing. You can check a lot of books and references that can be more accurate in the sense that I had to simplify it a lot to just talk a little bit of space weather and to have into mind some key points that we are going to later see in our modeling. Before start talking about our models, I want to talk a little bit of machine learning. I'm not sure how familiar are you with machine learning, because machine learning is something very like everybody talks about machine learning. I don't know if many knows really what is machine learning. So I put this little graph here that is you will see everywhere. What is artificial intelligence, machine learning, and deep learning. So the artificial intelligence is the whole area of the computer science that emphasizes the creation of intelligent machines that work and react like humans. So we are very far away of artificial intelligence. And a part of this a subset of artificial intelligence is machine learning. Machine learning are methods. So methods of data analysis. The idea is that we can have algorithms that can learn from the data and can find insights without explicit programming. So what we are going to do is